We saw examples of quantum circuits in the last video. This video will give you some theoretical concepts which will plug in the gaps in your understanding of quantum gates. Remember, we talked about universality in the case of classical circuits. We said that when we create a classical circuit, we say that we can pick gates from any universal gate set. What about quantum circuits? What gates are allowed? These discussions are kind of slightly more technical in the case of quantum gates. I have given them as extra readings in notes. If you're interested, please go through them and feel free to ask questions on the forum. What will be important for us would be to have intuition about what gates are allowed in a quantum circuit. For that, let's look at some examples, and by the end, we will have a few universal families of quantum gate sets and lot of gates which you can use while making a quantum circuit. Just a point of clarification, universal family in case of quantum means not the exact same thing which we meant in the classical case. The definition of universal family in quantum and classical is different. But I will leave more detailed discussion of this for extra reading. Let's worry about what kind of gates we can apply. You have already seen lot of them. You have seen Pauli, X, Y, Z, Hadamard, C0. And remember, for all these gates, we just specify their actions. For example, X is essentially a NOT gate extended by linearity. Y is given by this relationship. Hadamard takes 0 to plus and 1 to minus. Again, we are specifying action only on the basis states. You can do the same exercise for C0. Remember Z gate? What was Pauli Z? On 0, it leaves it as it is. On 1, it puts a phase of -1. If I want to represent it as a matrix, it will look like this matrix, which is very, very similar to identity. This is called a Z gate. You can easily calculate the eigenvalues and eigenvectors of all these operators. Using these gates, we can introduce more new gates. For example, I can talk about a phase gate. This is very simple, very similar to Z. Instead of 0, I get again 0, but if I have 1, instead of -1, I get I times 1. The matrix representation of this gate would be this. You can convince yourself by squaring that S is a square root of Z gate. Similarly, I can define square root of S, which is called a pi by 8 gate. The representation of this is 1, 0, 0 and e to the I pi by 4. You might be confused that I have pi by 4 in the entry here, but still I call it pi by 8 gate. The reason is that after doing some phase, I can write it as this. That's why it is called a pi by 8 gate. Using these definitions, we can also define These gates are x theta, which is e to the minus ix theta by 2, ry theta, which is e to the minus iy theta by 2, and similarly rz theta. These gates are very interesting because using these gates we can apply arbitrary unitary gates, or I should say or arbitrary single qubit unitary gates. Remember the meaning of this. This means that I'm applying this action on the eigenvalues of x. We have seen operator functions before. Once again, this is an example. We apply this function on eigenvalues of x. That's how you can make sense of this operator. You can write out the matrix representation of these matrices. These gates are important because, as I mentioned, any general unitary can be written as some phase and then application of Rz, Ry, Rz, where the matrix representation of unitary was so on. You will see that the exact form is not important. You can check it in the notes. The proof is given in Nielsen and Chang. An outline is given in the course notes. But the takeaway message here is that using Rz and Ry gates, I can calculate any single qubit unitary cheaply. In other words, if I can make these gates using any of our basic gates, then we can calculate any single qubit unitary cheaply. Not just that, if I have C0 gate and single qubit unitary, that gives me the ability to compute all unitaries up to any required precision. This gate set is universal in the quantum sense. I already mentioned that universality is different for quantum computing, quantum circuits as compared to classical circuits. But this is one complete gate set. And notice that single qubit unitaries can be replaced by Rz and Ry. If you read Nielsen and Chuang, you can get many more different gates which make universality. But for us, it is important to remember that whatever standard gate sets you have seen till now, I shouldn't say gate sets, but standard gates you have seen till now, they can be used in quantum circuits. You can use these standard gate sets, or you can make unitaries using these standard gate sets, and all of them will not be expensive. Another very important standard gate is CC0. This says this has two control bits, and the third qubit is applied if and only if first two bits are wrong. We saw an example of this application in the making a half adder. This is called a CC not gate. You have a lot of gates to choose from, and you will can read Nielsen Chuang and find out many more universal gate set families. But you don't have to worry about it. All the gates which we have discussed, you can use them freely in your quantum circuit. These standard gate sets are allowed. Another small thing to talk about quantum circuits is measurement. This is clearly different. There is no analog of measurement in classical circuit. We can simplify our circuits a lot by two observations or two properties whose proof I won't give. Again, the proof would be there in Nielsen-John. The first thing is that if we have measurements in between what will we do with these measurements? That means we will have classically controlled quantum operations after that. If there are things which we measure in between, they will only be used to classically control other operations. But it turns out this is equivalent to quantumly controlled quantum operations. In other words, without loss of generality, you can assume that all measurements are at the end of the circuit. When we prove lower bounds, when we say that, oh, you cannot make a circuit, we can assume that if you have made a circuit, you will only measure in the end. That's the most general class of circuits possible. Another thing, a small thing, you can always assume that any unterminated wire, the ones which we are not using, which we are not measuring, they are also measured. This will not affect the measurement statistics. At this point, you might not be clear about their applicability. Don't worry about it. We will, when we go to complexity theory, when we talk about a general circuit, we will see that these observations will be helpful for us. First one is really, really important, which says that you can always say, you can push the quantum measurements towards the end of the circuit without loss of generality. And second thing is saying that don't worry about unterminated wires, they can assume to be measured. We will remember these two important points. Then the two things which remain are universality, extra reading. Our takeaway is any standard gate set can be measured, can be used. Second thing is, what about classical circuits? It turns out that we can simulate classical circuits quantumly by using Toffoli gates, which are also called CC0. These are Toffoli gate. This shows that the power of a quantum circuit is more than a classical circuit, because any classical circuit can be simulated by a quantum circuit without much loss of number of gates. That means it's not expensive to simulate a classical circuit quantumly. The proof is not that difficult, and again it is given as an extra reading. This means we can assume any classical gate at our disposal with the same cost. Now, when we are going to do non-trivial operations in quantum computers, we are going to make our circuits. We can use any standard gate, and we can use any classical circuit. The cost of the classical circuit in the quantum will be the same as its cost in the classical.